Hello guys, hope all of you are doing great. In this part of the video, we'll be learning how to write a procedure to display negative numbers. In our previous part of the video, we already have written a procedure called display n that displays numbers on the screen, more specifically positive numbers on the screen. Today, we are actually going to modify or change this same procedure display n to take care of the negative numbers. See how to display negative numbers, how these numbers are stored in the memory, and all these details I have already explained in part 15 of this video series. So if you're not clear about those details, then I request you people to go to part 15 and see the details. Now, then also let me do a very quick recap of the main concepts there so that we are ready to write the code. So for that reason, what you need to understand is that, okay, suppose you consider a register, say 8-bit register, it could be a 16-bit register also. So, like if you store something in a register, they will be stored in this binary format. Okay. Now it is a matter of interpretation, whether you want to consider the value which is there in that register as a signed number or an unsigned number, in what way you want to interpret it. So if you want to interpret it, say for example, you're considering AL to be an unsigned number, in that case, the number is 11. There is nothing you have to check, okay? Just directly the decimal equivalent of that number. So 8 plus 2 plus 1 is 11. But if you consider it to be a signed number, then you have to do some checking. What is the checking? You have to check for this most significant bit. If the most significant bit turns out to be a 0, in that case, the value is positive. That means whatever it is stored there, the number is positive, and it is same as the content of the register itself. It is same as AL. You don't have to do any changes there. Okay. Say for example, if I say AL is this bit pattern, I'm considering AL to be a signed number, then what is AL? So in that case also AL will be 11. Now you see, suppose instead of storing this bit pattern in AL, we store this bit pattern in AL. So if you consider this AL as an unsigned number, okay? Now it is a consideration, what way you are interpreting it. If it is an unsigned number, then whatever it is AL, the binary equivalent, that itself is the value of AL. So it is, this is 11, and then 2 to the power 0, 1, 2, 3, 4, 5, 6, 7, 2 to the power 7 plus 11. 2 to the power 7 plus 11 is what? 2 to the power 532, 64, 6, and 128. 128 plus 11 is 9, and then 3, and then 139. If I'm not wrong, maybe it is 139 or something. Okay, so you don't have to do anything if you're considering it as unsigned number. That is the moral of the story. But if you're considering it as a signed number, if you consider it as a signed number, then what you have to do is you have to check the most significant bit, this bit here, most significant bit. Now you know here in this binary sequence, the most significant bit is 1. This implies this most significant bit is 1. This implies that the number is negative. Okay, and what is the value of the number? The number is negative, that you deduced. The value of the number will be you have to take the 2's complement of whatever it is in AL. This entire pattern, you have to take the 2's complement. So whatever it is, the 2's complement, that is the value of that that is the value which is stored in that particular register. So manually how to compute 2's complement. First take the complement, add 1. But here you see here in this process, what are two things that you need to know? See, you have to check for the most significant bit. Then how do you do the most significant bit? How do you get the most significant bit? That is one thing, and that you can achieve by making use of shift left instruction. This is your shift left instruction. So any register, you can shift left by 1 position, then that will tell you the most significant bit. Okay. And the other thing that you have to do is you have to take the 2's complement. 8086 instruction to take 2's complement is this negate instruction. Negate any register, say for example AX. So in that case, it will tell you what is the 2's complement of the content which is there in AX register. So this is just the overview. Okay, now we are ready to write the code. Okay, then let's begin. Okay, now we are ready to write the code. Say for example, we want to now display the number minus 3098, not 3098. And how to do that? Okay, So before proceeding further, I request you people, you please type this code if it is not already typed, because as I said in my previous part, I'll be modifying the same display procedure here, display and procedure here, to take care of the negative things, negative numbers. Okay, so I'm just doing a quick scroll up. If you want, you can pause the video and you can type this few lines of code. Few lines means 64 lines are there. You can type 64 lines of code. Suppose you have typed this code, then now you can start typing with me. Okay, now see what we want to do. We want to display these negative numbers there, no? So for that region, the first thing that we have to assume, we have to do is, okay, it is this display n is being called. Here is the procedure. Here we have to take care of it. Okay, we know the number is in AX. Now this time, since we want to like display both positive and negative, we have to take some decision. What decisions we have to take? Like, see, if AL we are considering as signed, it means first thing that we have to check is this most significant bit, and based on that we have to proceed. If it is 0, then directly the value is the value that we want to print. But if it is not 0, if it is 1, then first we have to take the 2's complement, and then that 2's complement value we have to display on the screen. Okay, let's see with code now. What we'll be doing is, okay, done. Now AX is the number. We want to treat AX as, you know, there's this AX, treat AX as signed. So we don't know whether the number is positive or negative. Okay, now how do we decide? So we have to take the most significant bit out. So for that reason, what we'll be doing is we'll be using shift left command instruction, actually shift left, and then this AX register by 1 bit. Okay, so if we do this thing, then it will set the carry flag if the most significant bit is 1. Otherwise the carry flag will be 0. That is, carry flag will be 1 if the most significant bit is 1. If the most significant bit is 0, then the carry flag will be 0. So it means what? We can now make use of this conditional jump instruction to do our branching. Now see what happens when the carry is set. Jump on carry, it means now that is, jump on carry means what? If we write something in jump on carry, it means that when the number is negative. Jump on carry true means the number is negative, because the carry flag is set, it means the number is negative. So what do we want to do actually? Jump on carry, the number is negative, so we just will write a block of code, and let's call that block of code as handle negative. Okay, say we will do something, and what are the something steps that we want to do? If it is 1, then the number is negative, and we have to actually do this extra step, taking the 2's complement. But before that, let's see if it is negative, then we understood. But what if it is positive number? That is, if the carry flag is not set, then the value itself is, the value is positive and it is equal to the whatever the initial register. I mean, you don't have to do any operation on it. Okay, so if it is carry, then we'll be handling it in this way. Otherwise it's a normal thing, so we can proceed normally. So let's call it, say, normal. If I needed to change the levels in future, I'll change it, but let's call it, say, from this point onwards everything is normal. But when you do normal, what we have to do is that see, before doing this normal, actually before doing this, say, okay, now let me put something here. See, we are doing left shift operator, so we have changed this AX actually, you know that. So normal is now not going to get the initial AX, our original AX, so that is lost because of this changing here. So for that reason, what we do is, before actually shifting this AX, changing AX, just we'll try to remember AX in CX register, say for example, just for a temporary moment, CX comma AX. Okay, just to remember AX. Okay, because we'll be needing it actually, and then we change AX, and then if it is negative, then we'll go to negative part and we'll do something there. And if it is not carry, then that is jump on not carry to normal. But the thing is, if it is not negative, basically what we want to do is we want to restore AX register from CX register. So you restore AX, okay, and then you proceed with this normal tag thing, and then you continue. Got it? Done. Now what if the number is negative? Okay, so handle negative portion we have to write. Jump on carry, handle negative. Let's say this is the block of code that we want to execute. If the number is negative, then what we want to do is, okay, handle negative. The number is first restore it. Okay, that's like restoring part. Move ax comma cx. We have restored ax. Okay, done. Then we have to take the 2's complement. Why did we restore? Because you see the number is actually 2's complement of the original, whatever it was there in the register initially before doing that shifting. So done. And then we have to take the 2's complement. What is the command for that? The negate command. Negate or negate instruction. Negate ax register. Done. You have taken 2's complement, and then that 2's complement you want to display on the screen. So then you want to actually jump to this point. You don't want to go to normal here, because you don't want to do this thing here. You just want to go to normal. So jump normal. Okay, that's done, I guess. See, jump on carry, handle negative. Handle negative is this part. That is, if it is a carry, then you basically want to execute restore ax, take the negation, that is 2's complement. This is basically 2's complement, 2's complement. And then once it is done, you go to normal, and from there, that is the normal thing actually. Okay, but this is handle negative. And then if it is not a carry, then what? Because you see, if it is not a carry, then also handle negative, it will be tempted to actually execute this handle negative. So if it is not a carry, we want to do this actually here. If it is not a carry, if it is a carry, it will go this, it will skip this line, it will go here. Okay, anyhow, we are restoring it, no? So there is no need actually this line here, I guess. Okay, jump on carry, handle negative. No, there is this need here. Sometimes I get confused. No problem. Jump on carry, handle negative. It will go there. It will restore ax and then negate ax, and then it will unconditional jump to normal. But if it is not a carry, then it will execute this line, and from there we want to do an unconditional jump to normal from here. Okay, and then normal means normal. Our ax is there, and it will do the normal thing. Now at this point, if I execute this program, you should be able to see that, okay, even if we interpret the number as a signed number, it will be able to give us this actual number on the screen. It means right now I'm not displaying the sign, but without the sign everything will be correct. It means if I store -3098 in ax register, and it should display me 3098 on the as an output. Let's see if we can reach that point, then most of the things are done, only few things will be left. So let's see, tasm this and tilling this and this. Now it is showing me 3098 and 6. See, if I store a positive number, then also 3098. If I store a positive number, then also 3098, and negative number, then also 3098. Things are working. Now only one thing is left, like the sign I have to display in front of the negative number, and that we know, this handle negative part, it knows, like, if the control is coming here, we know that the number is negative. Somehow we have to remember that thing. Okay, so how do you remember it? You can remember it in a variable, or you can remember it in a register. So I'll try to do it in register, but before that, let me check which register I have not used. I have used CX register, I have used AX register, DX register, BX register, SI register. Everything is used actually. What is not used? AX, BX, CX, DX, SI. I can use DI, destination index, and I think it will work. Let me store here. Okay, so I'll move. If the number is negative, then I'll store something in DI register. Okay, move DI comma something, like what I'll do. I'll store 1 there. Okay, and if it is not negative, then I will move to DI is 0. It means what? At some later on, if I check what is DI, and if it turned out to be 0, it means the number was positive. If it is 1, it means the number was negative. Okay, that's my point actually. Remember the sign. That's the region actually, okay, that I'm using this DL register. You can use a variable also if you want, but I just wanted to use a register. So DI was not used anywhere, so I'm using DI. Okay, done. Then where can I use this? Let's see. Right now the program should give you the output, I mean, as it was before. It should work fine, including those two extra lines. Has not changed anything about the program right now. Now what we want to do is that now based on this DI, wherever we are printing it, see, when we are printing it, we are like, when we do that pop operation, there we are printing the number, no? So this pop thing, let's or you see at the end we display the string. We first construct the string that way and then point the string by dx and then we print the string. So just before printing the string, we have to display the negative sign there, right? So here we'll be doing actually first thing is just do not directly print the string. Before that, we'll be doing a comparison. Compare DI, because in DI we stored that number, right? So we know, like, compare DI with 1. And if it is the case, jump on 0 or jump on equal. If both of them are same, it means the number is negative. So in that case, we want to display a negative number there, and otherwise we don't have to display anything, right? So jump on equal, or what we can do is jump on not equal. Okay, jump on not equal and the display string number, say, okay, and display string number is this, move bx comma dx. This is my display string number. So if they are not equal, then directly display string number. If they are equal, otherwise I want to do something here. And what is that something? I want to store move to DL this minus symbol, okay, that particular character, and then I want to move 0 to AH register. So how do I do that? Sorry, AH register 0 to H, and then I want to call int 21H. Okay, these 3 lines I want to do extra if the number is not equal to 1. If the number is equal to 1, see, if it is not equal, I don't want to do anything. It means it is 0, so the number is positive, no extra sign I have to display. But if the number is 1, that is if DI is 1, then I want to display the negative sign. So I'm doing this, and these 3 lines will display the negative sign, and after that the flow is normal. Got it? So this time if I execute the program, I should get, I'm sorry, what is this? If I execute this program right now, you should see the output should be minus 398. So is it minus or plus? What is this? It's a plus. So if I store a minus, then it should get me minus. Okay, it is showing me minus 398. Okay, so that's how we can display a positive number as well as a negative number. So if it is now minus 6, it's okay. We don't have to change anything in the code. It will simply, do the job. See, minus this and minus this. Done. And that is done actually. See here, I just once again I'm scrolling down the code, but here, before finishing the video, I have to tell you something very important. Okay, but before that, let me scroll down this code, and so that if you have not typed it yet, you can type it. Okay, that's all. These 88 lines of code. Now, there's something important that I want to tell you. You see, what is that important? Now, display number procedure. See, this, we are calling this procedure from some different part of the code, right? And then this procedure is executed. Now, see, this procedure, inside this procedure, we are actually changing the content of the registers in whatever the way we want. We're changing them actually. Say, for example, we used CX. We changed this DI, and then we changed this this CX register, DX register, BX register, and this SI register. You can see that actually, and this DL or DX register. Everything we're changing actually. And but the thing is that when suppose you just consider the situation that here you had move say si comma 89, and these si comma 89, once you call this display end function, at this point you cannot expect si to be like is si still 89. That question you don't know, because inside this procedure you have changed si quite a few numbers of time, isn't it? Like, you know, inside this display and procedure you can see, at least I can show you some instances where I changed si XOR si like this. See, I restored si to 0, right? As soon as I do it, there is only one si register, right? So if I reset it to 0, then obviously, although previously before calling this function it was 89, at this point you cannot expect it to be 89. It will be 0, or it will be whatever the si at the end of the execution of that procedure. We don't want that thing to happen, isn't it? Obviously we don't want, right? So for that reason, whenever you are writing a procedure, a good approach is that whatever the registers you are changing inside that procedure, you first make a copy of those registers in the stack, or that is basically you push those registers into the stack, and when you are done with the procedure you just pop them in the reverse order, and that way you will be restoring those values there. Okay, let me show you. So what I'm doing is that since I'm going to change all these registers basically, so I'll just do push ax register anyhow is the content. So anyhow, for that region also push ax register. Not only ax I changed sorry, I not only ax I changed bx also, I changed cx also, I changed dx also, I changed si also, I changed di also. Okay, so ax, then bx, then cx, so cx, and then dx I changed. Not only that, these source index register and these destination index registers, all of them I changed actually. Okay, and since I changed them, I pushed them into the stack. See, so when I do this pushing, you see here, which is at the bottom, if I do this push, you can see that like I'm going on writing this, no, push ax, then push cx, maybe dx, maybe no si. So in that case your stack will look something like this: at the bottom ax, then dx, then cx. Sorry, am I right? First ax, then cx, ax, then cx will come, then dx will come, then si will come. So if I do pop, I want to restore si, then I have to write it in this the reverse order: pop si, then I have to write pop dx like that. Okay, so that I can restore the values. So that's what I'll be doing here. So all of them in the reverse order. When the procedure is about to finish, where is it? It is here. You see, after displaying done, after everything is done, display the string pointed by dx. Suppose we do that. Now we restore. Then here just restore all the pushed registers. Okay, and how do we do that? I just have to do pop, but in the reverse order. Okay, just first we want to make a copy here, like store or backup all registers. Okay, that's all the registers which we'll be using inside the procedure. We'll be modifying inside the procedure. For all of them we are creating a backup, and then at the end we'll be restoring them. So where is my restore part? Restore all pushed register, but we'll be doing it in the reverse order. For that reason I just copied them. So first I have to do pop di, then I have to do pop si. So let me write them: pop di, pop si, and then I have to do pop dx, then I have to do pop cx, then I have to do pop bx, then I have to do pop ax, done. This pushing I don't need, I just copied them to si di. What is this? What is happening? It was initially push, huh? So push si. It was also push, I guess. See? Push di. So reverse order. See, pop. I lost it. this thing ax, bx, cx, dx, si, and di. Ax, bx, cx, dx, si, and di. So here, basically, I have to do pop di first, pop di, then pop si, then pop dx, then pop cx, then pop bx, then pop ax. Okay, so that way you have to do it. That is for safety reasons, so that unintentionally you don't change anything. Okay, so right now the program should give you exactly the same output it was showing you initially. So awesome. Okay, minus 3098 and minus 6. But this time what you can assume is that say for example si is 89 display function, although this display function or procedure is changing si because of that initial backup and then restoring the backup, at this point si is still 89. How do you check it? You just can do one thing. You just move whatever it is in si to ax register. Si, so move whatever it is in si to ax register, and then you call this display function. So because if si is 89, it will actually display 89 on the screen. Are you getting what am I trying to say you? I guess yes, no? So if 89 is still there, it means if we store si to ax and we call display n, it should display me an 89 there. And this 89, see, I stored before calling display n for the first time. Okay, let's see the output now. So let's go there and done. You see, in between this 89 is coming. It means we have stored 89, we call display n, although it is changing si, since we did that backup and restore thing there. So at this point si is still 89, and that's why this 89 is being displayed on the screen. So it's you see here, this is an important part there. So you always have to do that, you know, safety thing, like before changing any register, so that you do not mess up with the, you know, other part of the code. So whatever the registers you change inside a procedure, it's a good idea that first you create a backup of those registers, and once your task is done, before returning from the procedure, you just restore those registers from the stack. And how do you do this backup and restoring? Stack is quite a useful tool. You just push them into the stack at the beginning, at the end you just pop them from the stack in the reverse order. That's all. Okay guys, then that's all about printing a number. So we have now these you know, sort of foolproof display and function, display and procedure that can actually display both positive numbers and negative numbers, basically display signed numbers. Okay, so now in our next part of the parts of the video, like in the coming videos, we'll be using this procedure to write some you know, we'll be making use of this procedure actually. Okay, so this procedure will be copying to the next program, and then we'll be you know, assume that we have a procedure to display numbers, and then rest of the we'll do some other things there. Okay, like for example, displaying the content of an array, finding the minimum number present in an array and displaying it on the screen, and all those stuff. Okay guys, then that much only in this part of the video. See you guys with some new content in the next part of the video. Till then, have a nice day.